All right, so what is the limit of sine x over x as x goes to infinity? Let me just graph this function for you guys too, so we have some context of what this looks like. So y equals sine of x divided by x. Okay, so this is what that graph looks like. It kind of looks like a sine graph, but you can see that the amplitude slowly and slowly and slowly decreases as we continue on. And this is actually a very hard function to find the limit if we use substitution, if we use a regular limit rules, right? Like usually they're asking for this, basically, right? So limit of x approaching infinity when sine of x over x equals what, right? So substituting infinity into here and infinity into here, we get something very weird because this is a periodic function. So it's going to repeat over 1 and -1, and this is going to be infinity. So this is kind of hard. It's kind of hard to use our normal limit techniques to find our limit. So we're going to use something what we call the squeeze theorem or the sandwich theorem. So let me explain it to you guys here. Okay. So the squeeze theorem suggests that we can take, so let's say we want to find the limit. We want to find, let's say, we want to find the limit when x approaches the infinity of a function. Infinity of a function. Okay, but this function is very hard to use our normal limit techniques. So instead, we can find two simpler functions to squeeze between f and x. So what I mean by squeeze is that we can find function g of x, which is always going to be less than f of x, and we can find a function h of x, which will always be greater than f of x, right? So as I explained further, you guys are not just going to need to guess this function. There's a way to find these kinds of functions. But if you do find these kind of functions where the output of g of x is always going to be less than the output of f of x, and the output of h of x is always going to be greater than the outputs of f and x, the squeeze theory suggests that if the limits of g of x and limit of h of x equal the same limit, then the limit of f of x equals that limit. So this is what the squeeze theory suggests, okay? So we can use this theorem to help solve this limit, right? Because this is a very complicated limit and we can't just use the substitution infinity, we can't use conjugation, we can't use algebraic properties to try to simplify this limit, okay? So let's try. All right, so let's talk about sine, for example. Okay, for one, we know that sine of x is always going to be contained between +1 and -1, right? So we look at the function sine. Let me graph it for you guys. Sine of x. We always see that the range of sine of x is restricted to +1 and -1. There's never like sine x equals -5 unless you have some alterations to it. Okay, so we know that for a fact. Okay, so what if we divide everything in our inequality here by x? So what do we get? I'm not going to have a plus here. It's kind of redundant. Okay, so once we divide it by x, we have found a group of functions, namely 1/x and -1/x, that sandwich or squeeze sine x over x. This is just mathematically how that works. We can try to graph it out and see it, but by doing this clever trick, we have found two functions that sandwich or squeeze sine x over x, right? So now what is the limit as x approaches to infinity of negative 1 over x, and same thing for what is the limit as x approaches infinity of 1 over x, right? We see here that this equals 0, and this also equals 0. So now that we see that the limit of negative 1x, negative 1 over x, and 1 over x equals 0, then by the squeeze theorem, we know that the limit of x as x approaches to infinity of sine x over x equals infinity. So that's how the sandwich theorem works for the squeeze theorem. It's very, very actually useful for any of these sine or cosine functions where they're periodic functions. So yeah, that's how we use the squeeze theorem to solve this limit. Okay, so the junior student uses my solution, or I kind of use their solution, I guess. So this solution is correct. Good job. Cool. All right. Finally, we're going to